everyone, and welcome to Lesson 3.7, Applications of Periodic Functions. Now, many of you are probably wondering, why are we learning periodic functions? What application does it have in the real world? Well, actually, periodic functions happen quite frequently in the real world. You can take a look at ocean waves and tides. Those kind of represent a periodic function, or they can be modeled by a periodic function. Sunrise and sunset, all those types of things. So you can take a look at this list here and kind of realize that periodic functions are very quite practical, and a lot of these things can be modeled by a periodic function. Basically, to model any of these situations, we want to either choose to use a sine or a cosine function. Depending on the type and situation that you're dealing with, one is usually better than the other. So, for example, if in the context of the question you are starting at a maximum or a minimum point, it's probably better to use a cosine function. Conversely, if you are starting somewhere in the middle or at a midpoint, then a sine function will work better in that case. So we'll talk a little bit about that when we see some examples. So the first example we have here is the Ferris wheel problem. We're going to read through the question, highlight some important points. So it says the maximum height of the Ferris wheel above the ground is 35 meters. So that's a max point. That's important to us. I'm going to highlight that. So maximum height is 35 meters. It also says that it takes 2 minutes to make one complete revolution. This tells us the period. So from when someone gets onto the Ferris wheel at the bottom, makes one complete turn around the Ferris wheel, and ends up back at the bottom, that takes 2 minutes. It also tells us that people get on the Ferris wheel 2 meters above the ground. So that kind of tells us two things. That tells us a minimum, and it also tells us that our function starts at the minimum because passengers board the Ferris wheel at the bottom, which makes sense because no one's going to get on the Ferris wheel at the top. Okay, so we're going to take all that information and we're going to use that to basically model it in a periodic function. We want to write an equation to represent the height, so h of t, of a passenger from the ground at any time. An important thing to note here is that t is in seconds, and I'm going to reference that again in just a minute. So again, just like a couple of days ago when we were doing other lessons, a couple of things you need to create a function or a periodic function. You need your a value, your k value, your c, and your d. So that's what we're going to do right now. We're going to determine these variables, and then the other thing that we need to determine is whether we're going to use a sine or a cosine function. Now, we already talked about this for this particular question. The Ferris wheel, people get on the Ferris wheel at the bottom, so we get on at a minimum point, which means not only are we going to use a cosine function, but we're going to use a reflected cosine function. Okay, so if we start at a maximum, our a value for our cosine function would be positive, but because these passengers are getting on at the bottom of the Ferris wheel, we start at the minimum, so again, therefore, a negative a value. Okay, let's move on. So let's find or determine some of these periodic properties. Now the amplitude we find by taking the max value, subtracting the mid value, and then divide by 2. So the maximum value was 35 meters, and the minimum value was 2. So we're going to take those two, divide by 2, which gives us 33 over 2, or 16.5. So that's our amplitude. And again, because it's a reflected cosine value, we are going to use negative 16.5 for our a value in our equation. Okay, let's go on. Now the period. It told us that it took 2 minutes to make one complete revolution. But again, as I mentioned earlier, the equation wants t in seconds. So that's something to kind of take note of. So we need to convert that 2 minutes that it takes to make the one complete revolution into seconds. Okay, so in other words, one period is 120 seconds. Now remember that period is just 2 pi over k. Now this will help us find our k value. If we cross multiply, we will get 120k equals 2 pi, and then obviously divide both sides by 120, and that will give us 2 pi over 120, or in other words, pi over 60. So we have our a value, negative 16.5. We have our k value is pi by 60. Now, because we have chosen to use the reflected cosine function, we don't need to worry about any phase shift. Okay, so in this case, our phase shift is going to be 0. Then the last thing we just need to worry about is our vertical translation. We need to find our midline. Midline is calculated very similar to finding the amplitude, except this time it's max plus min. So we're going to go 35 plus 2 over 2, which gives us the 37 over 2. And in other words, we can change that to a decimal if you like to give us 18.5. Okay, so we have all the information we need. We have A, K, C, and D. So we're just going to put it all together. So an equation to represent the height of a passenger. So our function h at t is given to us as A, so negative 16.5 cos. So next comes our k value. So our k value was pi by 60, and then our variable t. We didn't have to worry about any phase shift, so nothing else inside this bracket. And then our midline, we shifted our function up 18.5 meters. So this is the function that we're going to use to answer a few follow-up questions. So part B says, how high is the passenger after 45 seconds? So basically what we're given here is a value for our time. So let's take our function from the last page, and essentially all we're doing is subbing in our value for t. So we want to find the height after 45 seconds. So our height at 45 seconds is equal to negative 16.5 cos pi by 60. Now here's where we're subbing in t. Remember, it's pi by 60 times t, so pi by 60 times 45, and then plus 18.5. So we'll simplify now. Negative 16.5 cos. Now remember, it's numerators times numerators, denominators times denominators. So essentially what we have here is 45 pi over 60. If we were to reduce that fraction, 45 over 60 would simplify to 3 over 4. So we're left with negative 16.5 cos of 3 pi by 4, and then plus 18.5. Now there's two ways that you can tackle this question. You can recognize that this angle here, this argument, is part of the special triangle family. So you can go ahead and kind of look back at lesson 3.2 and go from there and find out what cos of 3 pi by 4 is. The other thing you can do to save a little bit of time on the test, especially for a word problem, is to, number one, make sure that your calculator is set in radians, and then go ahead and punch in what you see. So negative 16.5 cos, open up a bracket, punch in 3 pi, actually use the pi button, divided by 4, close the bracket, and then plus 18.5. Now you should get an answer of 30.2 meters. Now again, using the calculator shortcut is only acceptable when you're doing word problems. If the question given to you on the test was simply just cos 3 pi by 4, make sure you go ahead and do those special triangles and draw out the diagram to get full marks on the test. Okay, let's move on. Next part, C says, if the ride lasts a total of 4 minutes, when will the passenger be at the maximum during the ride? Now, in this particular case, there's two ways to handle this question. I'll show you the short way and then I'll show you the long way. Okay, so based on what we know about the period lasts 2 minutes. One full cycle is 2 minutes. So halfway through each cycle, the Ferris wheel must be at its maximum height, or the person on the Ferris wheel must be at the maximum height. So common sense tells us that, well, if the ride lasts a total of 4 minutes, then after 1 minute, halfway through the first cycle, and after 3 minutes, which is halfway through the second cycle, then the passenger on the Ferris wheel must be at the maximum height. The other thing that we can do is, if we were asked to draw a graph prior to this, we could definitely see that clearly on the graph. The kind of longer way, which is kind of good to go through because not every one of these functions is going to be so neat and tidy that halfway is going to be such a nice number like 1 minute. So I'm going to kind of go through the longer way and kind of show you how to solve that. So basically, we could just set our height, h, equal to the maximum height, which in this case was 35, and solve for t. So let's go ahead and do that now. Again, let's recall our equation. So in this time, instead of subbing in something for t, we're going to sub something in on the left side here. We're going to sub it in for h. So set that equal to 35, negative 16.5 cos pi by 60 t plus 18.5. Okay, so our goal is to solve for t. Now, one thing to kind of note is that a lot of people kind of forget that cos must always have an argument. So this entire thing here, cos of pi by 60t, that is one number. So we're not going to separate cos from this bracket at all. It's not cos times this bracket. It's one whole entity. So back to solving for t. The first thing that we're going to do is move the 18.5 to the other side. So when we do that, 35 take away 18.5 gives us 16.5. Okay, then the next thing we're going to do is divide both sides by negative 16.5, which will give us a negative 1 on this side, cos pi by 60t. Now again, cos and its argument always go together. The only trouble for us is that t is inside that argument. So it's not like I can divide both sides by cos or anything to kind of get rid of this bracket. So what we're going to do now is we are going to just let this little part here, let the argument equal theta just for now. So let's pretend that this question really looks like this. Negative 1 equals cos of theta. Nice and easy. We can figure out what theta will give us a negative 1 on the cos graph. So if we go ahead and think about it, well, our cos graph looks something like this. And in radians, we have 0 radians at a maximum. At pi by 2 radians, we have 0. At pi radians, we have the negative 1. And then 3 pi by 2. And then finally 2 pi. Now, where on the cos graph does this happen to equal negative 1? Well, if you take a look, at pi radians, our function reaches that negative 1 there. So our value here for theta is really pi. Let's take that back to the question we were working on. The question we were working on said negative 1 equals cos of this particular argument. Well, we've already established that this argument must equal pi in order for this right side to equal negative 1. So let's go ahead and do that. Let's say that pi by 60t must be equal to pi. Well, now we just kind of cross-multiply and solve for t. So if I cross-multiplied, I'd be left with pi t equals 60 pi. And then if I divided both sides by pi, essentially they cross each other out, and we're left with t equals 60. So that tells me that just in one cycle, after 60 seconds, we would have reached our maximum, which kind of corresponds to our other answer above, after 1 minute. Okay, but the original question was saying if the ride lasted 4 minutes. So that tells me the Ferris wheel went around 2 times. So our job, again, is to find that second time that it reaches its maximum. So if it's at the maximum at 60 seconds, then basically if we add 1 full circle, if we add a complete revolution, then we'd obviously, kind of like finding coterminal angles, we'd find that other maximum point. So what we'll do with this is just add 1 full rotation, and we know that the next rotation, or 1 full rotation, is 2 minutes. So let's go ahead and do that. So first max is 60 seconds, second max is 60 seconds plus the 2 minutes, so 120 seconds, and that gives us a total of 180 seconds, which corresponds to our previous answer of 3 minutes. Okay. What we're going to do now is try and graph the function that represents 1 full ride for 4 minutes. So basically 2 cycles. The first thing we want to do is put in our midline. So our midline happened at 18.5 seconds. Okay, so there's our midline. The next thing we want to do is establish a starting point. So we've already talked about how this function is a reflected cosine, so we're going to start on the y-axis at the minimum. Now we said that the minimum was 2 meters off the ground. So there's our 2 meters off the ground. And we also didn't have to worry about the phase shift, so I'm actually going to start right on the y-axis here at 2 meters. And then we need to define our critical points. So we said that the period was 120 seconds. So to find our critical points, you just basically take that period, divide it by 4. So every 30 seconds, we're going to have another critical point, which you can clearly see on this graph here. So when our graph equals, or when our x value equals 30, we're going to hit our midline. At 60, we are going to hit our maximum, which is 35. The next critical point, back to the midline, and then finally, to complete 1 cycle, after 120 seconds or 2 minutes, back to the minimum. So you just kind of keep repeating that pattern, then connect the dots, and finally you will have your graph. Alright, so let's go ahead and try the next example. I would really like to do this one in class. Actually, this example does come up in a future lesson, so I'm just going to put this one to the side just for now. It's probably a good idea just to try it out, and we can take this up in class most definitely, but we're just going to kind of skip through this one, and I'm going to move ahead to our tsunami problem. So a tsunami is basically just a tidal wave caused by an underwater earthquake. It says, and here we're going to start highlighting, it says the water first drops from its normal level and then rises an equal distance above its normal level. So that tells me that because we're starting at this normal level and dropping above and below that, that tells me that this is probably going to be a sine function. It also tells us exactly what the period is, 15 minutes. In this case, we're lucky. We don't have to calculate amplitude. It is given to us. Amplitude of 10 meters. And it also tells us what our midline is. It tells us what that normal level is, and that's 9 meters. Okay, so it says assume that the depth of the water varies sinusoidally. Now, the word sinusoidally, because it starts with sine, a lot of people think that they must be using a sine function. And in this case, coincidence may have it that we are actually using a sine function. But all that sinusoidally means is that it rises and falls and rises and falls. It's like a periodic function. Okay, you don't have to use sine. But in this case, we're going to, because of all the evidence that suggests that. So the first thing we're going to do is sketch a graph. Again, start with the midline, which is 9 meters. So let's go ahead and do that. And the next thing we're going to do is establish a starting point. So we said the question suggested that it starts at this normal level. So that tells me that I'm going to be starting on the y-axis, no phase shift, at the normal level, and then we're going to drop off. So before I can find out where the minimum is, I need to determine what my critical points are. So it told us that the period was every 15 minutes. Take that 15 and divide by 4. So our critical points are going to be every 3.75 minutes. And maybe one other thing to note here as well that I forgot to mention is that this time we're working with t in minutes, not in seconds. So we don't need to convert this time anything into seconds. Okay, so after 3.75 minutes, because that's our first critical point, we should hit our minimum. The way that we calculate the minimum is given to us by our amplitude and our midline. The next critical point, back to the midline. The next critical point tells us to go to the max. So back to our graph over here, our next critical point has a maximum at 19, and then again back to the midline. So what I've drawn already here is our first cycle. We'll just kind of continue on with the function because we have the space for it. So next critical point, we reach our minimum. Next critical point, back to the midline. Next critical point maximum, and then again back to the midline. So then just connect all the dots and that'll give you your function. Again, we want to find the equation before we go ahead and answer any questions regarding that function. So let's find the equation for that first. And now again, we talked about this a few times. It starts at the normal depth. We're going to use a sine function. Now remember, a normal or a regular sine function with a positive a value will start at the midline and then rise. This one we're going to use a reflected because we started at the midline and then we went down to the minimum. So that tells us that our a value is going to be negative. We already know what the amplitude was. It gave it to us in the other page. So our amplitude was 10. We, in our function, are going to use negative 10. Okay, moving down. The period was every 15 minutes. Now, unlike the first example, I mentioned it already, we don't need to change these 15 minutes into seconds because it asked for t in minutes. So our 15 minutes, one full cycle, is equal to 2 pi over k. So that k is what goes in our function. We need to solve for it. Let's multiply both sides by k. That would give us 15k, and then just 2 pi on the right side. And then if we divided both sides by 15, we'd end up with a k value of 2 pi over 15. Because we chose an appropriate function, because we chose the reflected sign, our d value is going to be 0. No need to make it any more complicated than it needs to be. So the best thing to do is pick those appropriate functions so that your d value is always 0. And then finally, our vertical translation, well, that was, again, was given to us in the question. Normal level, or midline, is at 9. So let's take all of that information and plug it into an equation. So the height of the pier, h at t, after t minutes, is going to be the a value, so negative 10, sine, our k value was 2 pi over 15, and then our variable t, so 2 pi over 15 times t, and then plus the 9. So now we can use this function to answer a few other questions. So it says, what is the height of the water at the pier at the following times? So I'm just going to recall our equation here. And it's asking us to find the height of the pier, or the height of the water, at 2 minutes. So 2 minutes represents a time. We want to find the height at 2 minutes. Negative 10 sine 2 pi over 15 times 2 plus 9. So the first thing, again, we're going to simplify inside this bracket. So tops times tops, bottoms times bottoms gives us 4 pi over 15 plus 9. Now, in the previous example, we had a denominator of 4, which ended up giving us the option to use the special triangles or not. In this case, 4 pi over 15 is not helpful. It's not helpful to use any of the special triangle stuff, so it's just calculator work. Make sure your calculator is in radians and type in what you see, 1.6 meters. Okay, let's go ahead and try the next one. Now, one thing you can do at this point is, because we were already asked to graph, you can kind of take a look along the x-axis at 2 minutes, 4 minutes, and 12 minutes and see if your corresponding y values match what you got on the graph. One more question. It says to consider for tomorrow, but we're going to do it right now. It says, between what 2 times is there no water at the pier? So basically, we want to know when h at t equals 0. So similar to what we did in the first question, we're going to set h at t equal to 0, and we're going to solve for t. So basically, we want to try and peel away all of the layers, leaving us only with the sign and its argument, because again, sign and its argument are always attached. So I'm going to first move that positive 9 to the other side, leaving us with negative 9, and then we're going to divide both sides by negative 10. So negative 9 divided by negative 10 gives us, and again, what we want to do is we want to solve for t. So just for now, we're going to change up this question. We're going to let the argument just for now equal theta, so that this question now looks like this. 0.9 equals sine of theta. So this should be fairly simple. This is very similar to the work that we did a couple of days ago. We want to know what angles of theta will give us a positive 0.9. So first state, take a look at our quadrants, and first state which quadrant is sine positive, because we have a positive 0.9 here. Well, sine is positive both in the first quadrant and in the second quadrant. Ideally, if I was given a question like this, I would love for this ratio to be part of the special triangle family, so that I would be able to count by pi's and easily figure out what these related acute angles are. But not in this case. So in order to find out what these related acute angles are, I'm going to have to do the inverse of sine. So let's go ahead and do that. Let's call that theta related. Okay, so if I go ahead and punch that in on my calculator, again, making sure that your calculator is on radians, the related acute angle should be 1.12, rounded. Okay, so that tells me that the angle inside here is 1.12 radians, as well as this angle here, 1.12 radians. So just like in the other day's homework, we have 2 possible answers. The first answer comes from starting in standard position and rotating counterclockwise. So our first theta is 1.12. The second answer comes from, again, starting in standard position and rotating until you hit the terminal arm. So to figure out theta 2, we need to do pi minus 1.12. So our second possible answer is 2.02. Okay, so we're done our side work now. We've determined that theta is either 1.12 or 2.02. So back to our original question up here. It says, sine of what angle will give me 0.9? Well, if our angle is 1.12, we would get a ratio of 0.9. If our angle was 2.02, we would also get a ratio of 0.9. So essentially, this angle must be equal to 1.12. And now all we do is solve for t. We can multiply both sides by 15, leaving us with 2 pi t on the left side, and then 16.8 on the right side. And now if we take that and divide both sides by 2 pi, and evaluate that, one possible value for time would be about 2.67 minutes. Okay, so let's find the other possible value for time. Our angle should be 2.02. What value of t will give us that? Well, let's multiply both sides by 15, and then dividing both sides by 2 pi will give us 4.82 minutes. Again, a good way to check is take a look at the graph that we produced earlier. Well, here is our water level of 0 right along the x-axis. You can see that right here and right here are the values that we came up with, about 2.7 and about 4.8 minutes. We'll just make one concluding therefore statement and we're done the question. Alright, so that would be the end of this question, and in turn the end of the lesson. So if you have any questions, please make sure that you ask in class, and that's it for now. Take care, guys. Bye.